Welcome to the deep dive. Today, we're jumping into something really cutting edge, the intersection of machine learning and quantum computing.
It's a super exciting area.
Absolutely. I mean, think about how machine learning has, totally changed classical computing. We've got self-driving cars, amazing language translation, all this AI software.
Yeah, it's everywhere.
And for years, there's been this huge dream, right? To take that incredible learning power and basically put it onto quantum computers.
Right, harness that quantum advantage for AI. But that dream hit a pretty big snag for a while.
Okay, what happened?
Well, the obvious first step, or what seemed obvious, was to take classical neural networks, the things that work so well normally, and just kind of copy them onto quantum systems.
Makes sense. Try what works.
Exactly.
Yeah.
But it consistently failed. They ran into this big problem called barren plateaus.
Barren plateaus sounds bad.
It is. They're essentially mathematical dead ends.
Hmm.
Progress just stalled, completely halted.
Ah, the classic innovation roadblock. You try the old way on the new thing, and it just doesn't fit.
Precisely. But, and this is the exciting part, there's been a major breakthrough. A team at Los Alamos National Lab, led by Marco Cerezo,
Okay.
they found something huge. They mathematically proved a whole new foundation for quantum machine learning. Basically, they showed certain quantum neural networks can actually form something called Gaussian processes.
Gaussian processes. Okay, that sounds important.
It's incredibly important. It's like finding a whole new set of rules.
Yeah.
So for this deep dive, that's our mission. Figure out what these Gaussian processes are, why they solve this massive barren plateau problem, and what it means when people call this the holy grail of Bayesian learning for quantum AI.
So it's not just tweaking the old methods.
No, not at all. It's a fundamental shift, moving away from adapting classical ideas and towards building, truly quantum native models designed for quantum from the start.
This sounds like a great story about rethinking things. Have you ever faced a problem where you just kept hitting a wall with the same old approach?
Oh, sure.
What kind of thinking does it take to finally step back and find a totally new angle? This Los Alamos discovery seems like a perfect example of that.
Absolutely. It's about challenging assumptions.
Okay, let's dig into that copy and paste problem first. Why did it fail so badly? Talk a bit about how classical neural networks succeed.
Right. So classical neural networks are what we call parametric models,
Parametric, meaning?
meaning they have a fixed set of knobs, essentially, adjustable parameters or weights. Think millions of tiny computational nodes like artificial neurons.
Okay.
During training, you feed them data, and they tweak these parameters, these weights, to learn patterns. Each node makes a kind of educated guess.
And somehow that works.
It works incredibly well. Even if individual guesses seem a bit random, when you have millions of them adjusting over and over, the overall behavior, the output distribution, tends to settle into a predictable pattern, a Gaussian distribution, the bell curve.
The bell curve, right. So that convergence is key for classical AI learning.
Exactly. It lets them find averages, spot trends, make predictions. So naturally, researchers thought, great, let's just do that on a quantum computer. Quantum systems can handle way more complexity, so it seems like a perfect match for harder machine learning tasks.
But it wasn't.
Nope. As you said, the direct copy-paste failed.
Yeah.
Martin LaRocca from Los Alamos, who works on quantum algorithms, put it really well. He said, the issue with quantum neural networks is that we are copying and pasting classical neural networks and putting them in a quantum computer. This appears to not work as easily as one could have hoped.
Understatement of the year, maybe? So these barren plateaus, what are they technically? Why do they stop the learning?
Okay, so imagine you're training a regular AI. If the learning just stops, no matter what data you use or how you tweak it, that's frustrating.
Yeah, definitely.
In quantum, barren plateaus are like that, but worse, and kind of inherent to the structure for many proposed quantum networks. As you add more qubits, more layers, the space of possible solutions becomes unimaginably huge and incredibly flat. Yeah, flat. Think of learning as climbing a hill to find the best solution at the peak. In a barren plateau, the ground is so flat that the gradient, the signal, telling the algorithm which way is uphill, becomes tiny. Almost zero.
So the algorithm gets lost. It's no idea where to go.
Exactly. It's like trying to find the highest point on a perfectly flat, infinite desert at night. No clues, no slope. The learning just dies because the gradients vanish. This is tied up with the weirdness of quantum spaces, entanglement. It's complex, but the result was a dead end for many approaches.
Wow, that sounds incredibly frustrating for researchers.
Deeply frustrating. It really forces you to ask, like, what fundamental assumptions are we making that are wrong here? You can't just keep trying the same thing.
Which I guess leads us perfectly to the solution they found. Gaussian processes. You call them quantum native. How are they different?
Okay, so remember how classical networks are parametric fixed number of knobs?
Right.
Gaussian processes, or the GPs, are fundamentally different. They are non-parametric.
Non-parametric. Okay, break that down. Why is that the key?
Well, instead of trying to optimize a fixed set of parameters, which is exactly what gets stuck in those barren plateaus on quantum systems, GPs work differently. They model the probability distribution over possible functions directly.
Okay. A distribution over functions.
Yeah, they don't assume one specific type of function with a set number of knobs from the start. Their complexity can actually grow and adapt based on the data you give them.
Ah, so they're more flexible.
Way more flexible. And that inherent adaptability means they just sidestep the whole barren plateau problem. Learning can actually happen where these other methods were just completely stuck.
So let me get this straight. Classical networks sort of end up looking like a Gaussian bell curve after lots of training.
Right, they converge towards it.
But the Los Alamos team proved that for some quantum processes, you can essentially start with that Gaussian structure. It's inherent.
That's a really good way to think about it. Syriza, the lead, said their goal was to prove that genuine quantum Gaussian processes exist. They knew if they could do that, it would spur innovations and new forms of performing quantum machine learning, and they did it. Their math shows this bell curve behavior can describe certain quantum computations right out of the gate.
Okay, let's make this real. Diego Garcia Martin, the first author on the paper, called this the holy grail of Bayesian learning. He used a housing price analogy.
Yeah, it's a great analogy. Imagine predicting house prices. A typical neural network might just spit out a single number, like $500,000.
Okay.
A Gaussian process approach is different. You start by assuming prices follow some kind of probability distribution, let's say, a bell curve, a Gaussian. Now, you get some real data. This specific house sold for this specific price.
An observation.
Exactly. The GP doesn't just use that to predict the next house price. It uses that data point to update the entire bell curve. It refines your understanding of how all house prices are distributed.
Ah, so it learns the overall pattern better.
Precisely. And the more data you feed it, the sharper and more accurate that bell curve becomes. And crucially, it also tells you the uncertainty. It might say, okay, the most likely price is $510,000, but I'm 95% confident it's between $480,000 and $540,000. That uncertainty measure is huge. This whole approach is called Bayesian inference, using Gaussian process regression.
And Garcia Martin said the same idea, this Bayesian approach with uncertainty, can now be used in quantum computing because of their proof.
That's the breakthrough. It unlocks the power of Bayesian methods for quantum systems. And think about why that's so vital. In quantum, you're often dealing with probabilities inherently.
Right. Things aren't always certain.
Exactly. So having a machine learning model that not only predicts but also tells you its confidence or uncertainty is a much more natural fit. It's perfect for dealing with noisy current quantum computers, the NISQ era devices, or situations where you just don't have much data.
That feels really powerful, not just getting an answer, but knowing how sure the system is. Imagine applying that refinement, that uncertainty quantification, to something like drug discovery.
The huge implications. Predicting molecular interactions. Getting that wrong costs millions years of research. Knowing the uncertainty could guide experiments much more effectively.
Or climate modeling. You need to constantly update models with new, sometimes noisy data. Understanding the confidence in predictions about complex systems is critical.
Absolutely.
It makes you think. What challenges in your own field, or maybe just everyday problems you try to solve, could really benefit from an approach that learns and tells you how sure it is? I'd love to hear what you, our listeners, think about that. Where could this kind of adaptive, uncertainty-aware learning make a difference?
It's a great question. It changes how you think about prediction.
So, stepping back, what's the big picture here? What does this mean for the future path of quantum AI?
It's a genuine paradigm shift. Marco Cerezo really nailed it when he said, we need to find new ways of doing quantum machine learning, not continue to beat a dead horse, so to say, by recycling old methods.
Stop trying to force the old square peg into the new quantum round hole.
Exactly. This research is a huge push for the whole quantum community to think differently, to develop new models, tools designed for quantum, instead of just trying to make classical ideas work where they clearly don't. or at least not easily.
And this wasn't just an overnight thing, right?
Oh, no, not at all. This is the result of years of hard work, lots of dead ends probably. Being able to replicate the learning power of classical networks on quantum machines has been a major goal for a long time. This paper is the first time anyone's mathematically proven this kind of Gaussian process capability exists in the quantum realm. It's a new blueprint.
It also makes you wonder, like Cerrizo's beating a dead horse comment. How often do we do that in other areas? Sticking to old ways when a new technology or situation really demands fresh thinking.
It's a common trap, I think. We get comfortable with familiar tools.
So let's be clear, quantum computers aren't quite ready for prime time yet, are they? This work is still largely theoretical.
That's right. We're still in what's called the nascent technology phase, early days. So yes, the Los Alamos work is theoretical groundwork right now. But, and this is really important, it's absolutely crucial groundwork.
Why crucial now, if the hardware isn't ready?
Because when powerful, reliable, error-corrected quantum computers do arrive, and the consensus is we need to have the software, the algorithms ready to go. You can't wait for the perfect hardware and then start figuring out how to use it for complex tasks like machine learning.
You need the theoretical tools ready and waiting.
Exactly. We need these powerful quantum-native machine learning models developed so we can actually use quantum computers to tackle those incredibly complex problems, the ones classical computers just choke on, the intractable problems.
So this isn't just a paper for quantum physicists, then?
Not at all. Think of it as laying the foundation for future solutions. Imagine accelerating the discovery of new materials, maybe room temperature superconductors, or optimizing global supply chains in ways we can't even conceive of now, or simulating molecules for drug discovery with perfect accuracy. This kind of foundational work makes that possible down the line.
It really does make you question assumptions. What other big challenges out there might need us to go back to basics, challenge the old ways of thinking, especially as new tech keeps emerging?
That's the billion-dollar question, isn't it?
Okay, let's wrap this up. What an incredible journey today. We started with this huge promise, quantum machine learning, but saw how just copying classical methods led straight into those frustrating barren plateaus.
Right, the dead ends.
Then we explored this really elegant solution, Gaussian processes, a truly quantum native approach, mathematically proven now by the Los Alamos team, that sidesteps those old problems. It's not just a fix, it's a whole new way of thinking.
Absolutely. It's a mindset shift towards building for quantum, not just adapting from classical.
And this isn't just some, abstract math exercise. You've convinced me it's a solid, proven path forward. It gives us the theoretical tools we need to eventually unlock the real power of quantum AI.
That's the hope. And now it's backed by rigorous proof. It ensures that when the hardware matures, we'll actually have sophisticated, well-understood algorithms ready to run on it, algorithms designed specifically for that quantum environment.
So as we finish, here's a thought to take away. We saw that copying and pasting classical ideas didn't work for quantum machine learning. It needed a native solution. Where else might we be stuck? What other areas, maybe in technology, maybe even in everyday life, are being held back because we're just trying to force old solutions onto new kinds of problems? Where could a truly native approach, something designed from the ground up for today's or tomorrow's challenges, lead to breakthroughs we haven't even imagined yet? Something worth mulling over.